Welcome to Study Loop.
So in this process where the air enters turbochargers and then from turbochargers it goes into an intercooler, turbocharger essentially is allowing air to expand in volume under constant pressure. So for this sequence of the process, some constant pressure will be here, P0 for example, and then V0 or V1 to V2. It expands like this. So it will be 0.1, 0.2. This is the turbocharger phase. Now, from 0.2 to 0.3 is the intercooler phase, which is the phase where the gas is rapidly being cooled and its pressure decreases, but volume increases further. So some volume, V3, and this is an adiabatic process, so it will look like this, adiabatic curve, 0.3, and this would be the PV diagram for this sequence of the process where the turbocharger and the intercooler are doing their work on the gas before the gas actually enters the cylinders of the engine. This is for the part A of the problem. Now, for the part B of the problem, so the temperature is overall is constant through the process, while the density is proportional to the absolute temperature. So in this case, we can say that the mass equals density 0 volume times the ratio of the pressures, where PA is the atmospheric pressure. So to find this mass, we can and we should directly substitute the known values. So this will be equal to 1.23 kilograms per meters cubed times 575 times 10 to the minus 6 power meters cubed, and then times the ratio of the pressures, which is 1.45 over 1.01. This is an approximation for the atmospheric pressures, and when we evaluate this using a calculator, we obtain that mass equals 1.02 times 10 to the minus third power kilograms. And to compare between the pressures, we should find the percentages. We should say that P minus PA over PA times 100. So this is the standard formula for evaluating percentage differences between two arguments or two values, in this case P and PA. So this is equal to, when we substitute the values, 1.45 minus 1.01 over 1.01. The part where we multiply this with 10 to the 5th power pascals will cancel out. So we're using only these numerical values, and this times 100, and this equals 245%. So this is the solution to the part B of the problem. Now for the part C and the last part of this problem, we need to actually find the mass ratio in percentage. So this is why we evaluated the mass in the first place. So here, to get the mass, we need to find the change of density due to pressure difference inside the adiabatic process. So this different density is equal to initial density times P2 over P1, 1 over gamma. Substituting the known values, we obtain that this is 1.23 kilograms per meters cubed, and here is 1.45 over 1.01. 1 over 1.4 since the gas is air. And this equals to 1.59 kilograms per meters cubed. So when this compression happens, the density clearly increases. Now the mass corresponding to this density is equal to, of course, rho times the volume, which equals 1.59 kilograms per meters cubed times 575 times 10 to the minus 6 power meters cubed, and this equals to 9.16 times 10 to the minus 4th kilograms. So finally the ratio of change in masses is this ratio. So also we need to multiply this by 100 to get the percentage value. So this will be equal to 9.16 over 7.07, and both will be times 10 to the minus 4th power, so this will cancel out, and also the part where the units of kilograms will cancel out. Notice this will be minus 1. This needs to be minus 1, and then times 100. This minus 1 part comes from the general formula for percentage evaluation, and this is equal to, I will actually use the red color here, this is equal to 30% of change. So the mass changes this will actually be the change of the powers, because corresponding to this change of mass, the power will also change for 30%. So we can say that here the power increases for 30%, and with this change of mass that is in part B, the power changes for 44%. So these changes in mass and pressures due to intercooler and turbocharger are actually increasing the power of the engine. So this is the increase of power. So we have solved all parts of the problem, and I hope you find this helpful, and I hope to see you in another lesson.